Hi folks, this is Calc 1, Checkpoint Quiz 4. We're given a piecewise defined function f of x. We're asked to state the intervals of continuity. So the first thing we do when we're given a piecewise function is we check each of the pieces. X squared minus 1, 5, and x squared plus 1 are all polynomials, so they're continuous everywhere. The only thing that could screw up then is at this point x equals 2, which is where we've broken the domain. So what does it mean for a function to be continuous at 2? Well, to be continuous at 2, the limit as x goes to 2 of f of x has to be the same as f of 2. So that says that the limit not only has to exist from the left and right and agree, but it also has to equal the actual function value. So let's go off and investigate the limit as x approaches 2. Well, first off, let's do f of 2. Check that first. It is defined, f is defined at 2, it's defined to be 5. Now let's investigate the limit. Well, since we're broken up into pieces, we need to approach from each side and see what's happening from each side. So we'll take the limit as x goes to 2 from the left of f of x. And remember, what we're thinking about is we're thinking about numbers a little bit smaller than 2. So 2 minus a little bit. 1.9, 1.99, etc. And so that means I'm going to be using this formula, because that's the formula for the x's when they're less than 2. So that's the limit as x goes to 2 from the left of x squared minus 1. That's a polynomial. We can use the substitution principle. And we get 4 minus 1, which is 3. So we already know we're in trouble, because as I come in from the left, the limit is 3, and that's not the same as 5. So at this point we know the function is not continuous at 2. However, maybe it's continuous from one of the two directions. Let's look then as we come into 2 from the right. So now we're plugging in numbers that are 2 plus a little bit, so things that are a little bit bigger than 2. And when x is greater than 2, we use x squared plus 1. Since it's a polynomial, we can just use the substitution rule, and that gives us 5. So as we come in from the left, we get 3. As we come in from the right, we get 5, and that matches the function value. So what's happening graphically at 2? As we come in from the left, we're coming close to 3. As we come into the right, we're getting close to 5. And the function value at 5, or excuse me, as function value at 2 is equal to 5. So we have this sort of phenomenon happening here. Okay, so we have a jump discontinuity. So this is what we call a non-removable or essential continuity. So it's not continuous at 2, but it is continuous from the right at 2, because the limit as x goes to 2 from the right equals 5, which is the function value at 2. So for intervals of continuity, what are they? Well, it's continuous from negative infinity up to 2, and it's continuous from 2 to infinity, but we're going to include the 2 on this interval only, because what we're saying with this interval is that it's continuous from the right. At x equals 2. In other words, or the limit as x goes to 2 from the right of f of x is f of 2. Okay, so that's the intervals of continuity for f. Okay, number 2, we're asked to find and classify the discontinuities of this particular function. If the discontinuity is removable, we're supposed to redefine the function so it is continuous at that point. So, discontinuities. Well, for functions like this, the discontinuities are going to be the places that aren't in the domain. The sign of pi x is fine everywhere. 2x squared minus x minus 1 is good everywhere. The only thing that could screw things up is if that denominator is 0. So that's where we're going to go find our discontinuities. We factor. Oops. if I could factor correctly. We have 2x plus 1, x minus 1 is 0. That gives me x equals negative 1/2, as well as x equals 1. So these are where the discontinuities are going to be located. So the function is discontinuous here. Now to determine what manner of discontinuity, what kind of discontinuity it is, we need to look for the limit. So that's what you got to remember. Removable discontinuities, the limit exists. The non-removable or the essential, the limit does not exist. Because to be removable, we have to essentially just be patching a hole. And for that hole to be in the right place, for us to patch it, the limit has to exist. So let's check around x equals negative 1/2. So we take the limit as x runs off to negative 1/2 sine of pi x over 2x squared minus x minus 1. And the first thing we always try when evaluating limits is substituting in the given value for x. Well, if we plug in x in the numerator, I get the sine of negative pi over 2, which is negative 1. When I plug in negative 1/2 on the bottom, well, I get 0. And I know that because I said equal to 0. So we have the form negative 1 over 0. And that's not going to give us a limit. So this limit does not exist. If we wanted to be a little more precise about it, we could approach negative 1/2 from the left, negative 1/2 from the right, and see which infinity it's heading off to. But if you have a non-zero number over 0, that limit's not going to exist. So what does that mean? The discontinuity at x equals negative 1/2 is essential. In fact, if you go through the analysis, you see you're going to get a vertical asymptote there. So x equals negative 1/2, it's an essential discontinuity. There's no helping it.